Well, hello, everyone. I'm Dan Work. I'm an associate professor at Vanderbilt University in the Civil and Environmental Engineering Department. I work on a lot of problems in traffic and really trying to understand the impacts of connected and automated vehicles. So I'm going to do the impossible task today of trying to give at least some inspiration for why people in traffic engineering care about connected and automated vehicles. And in particular, the roadmap that I've got outlined for today and also in the second part of this talk that we'll carry on next week, is basically trying to give some super high-level context. If you're not deeply ingrained in the transportation engineering community, why on earth people in transportation are keen on connected and automated vehicles, despite their obvious potential limitations. And then I want to talk a little bit more about the data that Benny mentioned in the earlier talk in this session. What's available today, what's coming online, and what these data sets might help us do in terms of managing traffic, specifically on the estimation side. And on the second part of the talk that we'll carry on next week, I really want to go into detail in terms of what that means for traffic control. So that's the high-level roadmap. The general problem that people in transportation deal with is trying to move goods and people. Obviously, a lot of us are focused on the movement of people side because that's what we as users of transportation systems experience. But there's a huge part of transportation engineering that deals with efficiently moving goods. And that is ever so important, especially in the context of supply chains and making sure that things around the world get delivered to you in a timely way. Well, these issues in transportation centered around moving goods and people have always been there, whether it was dealing with the technological innovations that were happening on the farms in the Midwest, at the turn of the last century, or whether it's the innovations that are happening in the orchard fields in Silicon Valley as people are trying to figure out how to put a modern spin on delivering goods and making people move efficiently. So I would argue that this question about how to move goods and people efficiently is actually not that difficult until you start adding in like the actual complexities of modern transportation systems. And what I have in mind there is really trying to deal with designing and managing these transportation systems that both respect the users of those transportation systems and the planet in which they operate. And so as you look at the actual problems in transportation, it's really driven a lot by some of the consequences that you have when you operate transportation systems in the real world. So the Transportation Research Board of the National Academies produced a report that outlined some of these critical issues in transportation in 2019. And they span the spectrum from how you actually govern these systems, recognizing that transportation systems in the United States historically were mode-driven, but the more that we use multiple modes to travel from one place to another, the harder it is for these agencies to address these challenges. You can even think about public-private roles right now as you have transit interacting with rideshare services and so on. Resilience and security have always been an issue in transportation, but now more than ever. And really trying to understand the equity issues of transportation systems in terms of who gets access to what and where, and how to use these systems to provide access to more people is definitely going to be important, especially as the population continues to grow and shift in terms of its demographics. So these are the meta problems that have our field really up at night trying to think through. And I think it's worth, as we go through the long program at IPAM, to really challenge ourselves to figure out, when you think about connected and automated vehicles, what are the potential implications on some of these critical issues? Where can we make a difference? And where, if we're not careful, will connected and automated vehicles exacerbate existing problems? For the focus of the tutorial pieces here, I'm going to talk more specifically about a couple a shorter list of some of the issues, in particular around safety and public health and energy and sustainability, and really look at what these transformational technologies, connected, automated vehicles might do in those spaces. Okay, so it's easy to get caught up in the buzz of automated vehicles, but I want to take a step back and actually ask why we do this. And I think one of the promising areas for connected and automated vehicles is to try to address this extremely high cost of transportation systems not working well. If you look at the global statistics in terms of crashes and fatalities, there's 1.2 million people annually that die in car crashes. There's more than 50 million people that are involved in serious injury crashes. If you take those statistics around the world, you can see some statistics here from the World Health Organization in terms of how many deaths per 100,000 people you have due to driving on the roadways. So it's a real issue to use automated vehicle technologies to try to reduce that threshold. But if you want to make a difference, you actually have to know what the causes are. So it's estimated that in 2030, that crashes will be the 7th leading cause of death in that year. I mean, that's pretty remarkable that that type of issue would still exist. But then you look at the causes. The causes for crashes are related to a lot of behavioral factors: speeding, drunk driving, not wearing a seatbelt, not having child restraints, not wearing a helmet on a motorcycle. And so if you put that on the board and then ask what automated vehicles are going to do for those factors, an automated vehicle will not put a helmet on a motorcycle driver, right? So we need to be very careful about how we design those technologies and which of these factors they might have an impact on. And then just to really double down on this point that not every problem is one that technology can solve by itself. If you look at the population globally and what people live in communities that have laws that govern these major crash factors, only 7% of the population lives in a community that has laws that actually govern all of these major factors. You let that settle in for just a second, that 93% of the people live in communities that don't have laws that do things like make you wear a seatbelt, wear a helmet, have low alcohol limits in terms of what's allowed to be operating a motor vehicle and so on. Okay, so I think that's definitely important to consider. And then if you find yourself in a particular population, namely people between the ages of 15 and 29, being in a car crash is the leading cause of death for people in that cohort. So you may really want to think carefully about which problems you tackle in your PhD and what they might do for road safety. Okay, so where are we making progress in road safety? In particular, we're making strides in a concept that came out of Sweden known as Vision Zero. And the idea there is really to think about the fact that users are going to make mistakes. And those mistakes should not be fatal. We need to design the systems that account for the natural failings of humans and not punish people with loss of life. So designers design the system, users are going to use those systems, and if things fail, you fix the design. You don't blame the user, right? And some of the key ideas that are in there is that actually saving lives is not that expensive. If you happen to be in a Vision Zero community, you may recognize these types of signs or seen things where the speed limits in your neighborhood have been reduced. Part of the reason is that if you design these systems in such a way that a crash does not exceed the tolerance of what a human can handle if they're involved in a crash, you're much more likely to survive. So these pictures show things like, well, if you are hit by a vehicle traveling at 20 miles per hour, well, 9 out of 10 people survive those crashes. But if you live on a road or walk on a road, as I do, with a speed limit of 30 miles per hour, if I get hit by a car driving in my neighborhood, my chances of dying went up from 1 in 10 to 5 in 10. And as the speed limit increases, the chances of survival just diminish rapidly. So simple things like, you want to reduce the number of crashes globally, reducing the speed limit and enforcing it is something that is not wildly expensive and far out of reach of today's technological systems. It's available today. So it doesn't have to be expensive. And these types of ideas, they do work. Sweden is most notably the success story that pulled their crash statistics from one of the highest in the world in high-income countries to one of the lowest in the world. So, in the U.S., I think there's definitely a caveat that one should have when you look at these types of statistics, which are deaths per 100,000 people. Obviously, some communities drive substantially more than other communities. So if you normalize these by vehicle miles traveled, you'll get a different ranking. But still, I think the main message is the same, that there are things that we can do that don't require connected and automated vehicles to improve very real problems. Vision Zero is now moved to many communities in the United States. And so you can go onto the US Vision Zero network and see which communities have started to adopt these ideas. Okay, so that's a lot of the soapbox, but what can connected and automated vehicles do? Well, can those vehicles partially address some safety issues? And I think the answer there is yes. There was a study done in 2016 that looked at what types of vehicle automation technologies are already available on cars, and just looked at crashes in the United States and took an optimistic viewpoint, and it's carefully documented in the paper, so it's not meant as a criticism, but took an optimistic viewpoint and said, okay, well, if you were involved in a crash that potentially could have been avoided with a blind spot monitoring system, we'll assume that a blind spot monitoring system would have allowed you to intervene and prevent that crash from occurring. So then it just looked at broadly, what's the upper bound in terms of crashes and fatalities that could be saved with the basic stuff, blind spot monitoring, the thing that flashes a light at you if there was a car in your blind spot, or lane departure warnings. If you've got a modern car, it may nudge you back into the lane as you start drifting out of your lane, or at least alert you that that is occurring. Same thing with forward collision warning. If you're getting too close to the car in front, where if it brakes, there's going to be a collision, it will either alert you or in some cases actually intervene. And so if you look at the statistics, something like 32% of the fatal crashes could have potentially been avoided with these types of technologies already on the vehicle. So we're not talking about complete brain-off driving. We're not talking about a car that can, drive across the country without human intervention, no steering wheel, no gas pedal. We're talking about cars that you could essentially buy today if they have the right type of safety features in them. These could actually make a measurable difference in terms of the crashes that are on the roadways today. Okay, so I want to switch gears a little bit and talk more about the technological innovations that are happening in this sort of nexus of people, infrastructure, and the internet. In terms of how the technologies have rolled out, connected and automated vehicles sits right at this gap between technologies that are already available today and are really easy to deploy, and technologies that are going to take an awful long time to get into the infrastructure. So we have systems based on the rapid development of the smartphone that basically took us from dumb maps where we didn't know anything about the traffic conditions to real-time traffic maps. We can route around traffic. Kind of the fun and new spin that folks are playing with on the phone-based tools is that relates right back into the safety space, is using the phones to do things like try to nudge you to become a more safe driver, nudging you if you're accelerating or decelerating too aggressively. There's even an app now that does crazy things like reads the license plates off of the cars that are in front of you and will let you know if the person in front of you is known to be a risky driver. You can imagine what car that phone has the most data on. It's probably not the car in front of you. It's your own car, obviously, because it's tracking your accelerations, your speeding, and things like this. The reason that the phone really drove the innovation in the transportation landscape so early on is because we got rapid market penetration very quickly, and the phones just last much less long compared to cars. So I can't even remember the phone I had a decade ago. I'm still driving the same car I had a decade ago. As you sort of fast forward and start thinking about, when will our automated future be here? I think this question of how you deploy at scale these technologies is always a challenging one. There are maybe to challenge the assumption that the rollout will be slow, which I actually think it will be. There is a counterpoint, which basically says that if all the vehicles are automated, at a transformational technology level, then people will ditch their vehicles overnight. I don't know, if you've got a fleet vehicle, it might put 100,000 miles on a car in a year, which might make it prime for a complete refurbishment at the end of the year to get the latest and greatest technologies that have been developed over that 12-month cycle. But for most of us, I think it's going to be more realistic that, we might not have some of those technologies in our vehicle until we replace our vehicle again, and we won't replace them based on the latest technology attribute on it. We'll wait until our current car no longer functionally serves that use. Well, if you think the car tech is slow, go look at the infrastructure tech. A lot of the technologies that have been proposed in the connected vehicle domain specifically have just run right up against the challenges of trying to get that technology, one, on the car, but two, on the roadside. If you've got to have infrastructure upgrades at intersections so that the traffic light can talk to your car, or roadside infrastructure so that your car can communicate to cars that are further away than direct line of sight communication would allow, then you need some roadside infrastructure to do that. And the infrastructure is just glacial in its time scales. In road engineering, you might build a bridge that can last for a design life of 50 years before it needs major upgrades or major repair. Thinking about that at an internet time scale where we're pushing new software in real time, those things are just completely incompatible. It's very challenging to design infrastructure that can persist for decades and still be accommodated from technology upgrades. And just to prove that point in even more detail, we know how to design traffic signals that are smarter, that can respond using sensors that are nearby, including video cameras, to adjust the traffic signal timing. But still, on the order of above 90% of the traffic lights in the United States work on a kitchen timer, more or less. There's a clock inside the control signal, and every n seconds it swaps it from green to red. And part of the challenge is that it's not like we don't know how to do it. It's just extremely expensive to get to all of those intersections and upgrade them, especially if you have to cut concrete or drill holes in the ground or things like this. It's very slow and very cumbersome. So I think what excites me today right now is that there is so much work happening in the vehicle automation space that is starting to allow us to rethink not only how these technologies might impact safety, but other things we might be able to get out of them in terms of traffic management, in particular traffic estimation and traffic control. And some of these benefits will be here long before the so-called self-driving car, level 5 brain-off driving is available. I put this 5+ years of when it will be available because I think the earliest record I saw was something in the 30s that said that the cars would be automated in 5 years, and about every 3 years you get an upgrade in terms of when that 5-year prediction will be there. But no question, the innovation that's happening today is rapidly advancing this field. So what are the mobility revolutions that are happening today? In Benny's talk, he briefly mentioned the so-called revolutions. This term was coined by Dan Sperling in 2016. The three revolutions are electrifying the vehicle fleet, automating and connecting the vehicles, and the whole sharing economy where you do things like rideshare in the conventional Uber and Lyft to the future where you might actually use a fleet of automated vehicles. For me, I think the main thing that I want to emphasize here is that as these revolutions are unfolding, it's going to be really important to monitor how they unfold and then actually control them or steer them into the directions that we want so that we get positive outcomes of the systems. I think I know that the physics of the traffic system will change when you put automated vehicles in them. They will change when you allow vehicles to respond to information that a driver cannot see. And I think we need to be very careful about designing those technologies in such a way that those technologies don't do things that are locally good for one driver, but globally bad for all drivers. And through the course of the IPAM program, I think we're going to see several examples of settings where one can do things that are locally good, but actually globally bad for traffic overall. So the sort of challenge that traffic engineers are often faced with is trying to deal with stuff like on this video. How do you control this traffic? How do you monitor this traffic? And how do you get that information back to users in a timely fashion so that they can actually change their decisions based on that information? I guess instead of showing cars driving in circles, if you watched Benny's talk, he quoted George Box. I think that point was made quite clearly. The typical framework in which we look at modeling our transportation systems, we start with the real system, and then we make some abstraction from that system. We write a partial differential equation to describe the traffic dynamics, or we build some discrete choice model that characterizes how humans make choices and make decisions about what modes they might take. But we basically build some kind of model abstraction, and then we use that abstraction to analyze, to compute, to study, to explore sensitivities, to consider what-if scenarios. Very valuable, but often those models require things that are hard to get precisely, whether it's the initial conditions of the system or the boundary conditions of the system or the parameters that govern the behavior of the system. Those things are unknown in some cases, and yet really important to characterize, because if you get those things wrong, then this model stops looking like your real transportation system and more like a computational experiment that is inspirational but not directly tied back to the real world. So what people obviously have done is they've said, well, like in an abundance of sensor data, maybe we, don't need these models. In fact, most provocatively, I've got this quoted to two different people. Chris Anderson misquoted Peter Norvig in a Wired article and basically said that all models are wrong and increasingly you can succeed without them. That obviously is not a true statement. Even if you're doing machine learning or building some other kind of data-driven system, you're building a statistical model. It's not a first principles model, but it's still a model. And so those models are still very helpful for analyzing these systems. But this idea that you could potentially get rid of the, quote, model is driven by the idea that there would just be so much sensor data available that you directly know what's happening in the real world. Of course, the reality is that those models are still good for making predictions. Those models are still good for testing things that are not yet observed, and helping your data-driven models generalize, helping your physics-based models explore scenarios that you haven't operated in. But kind of the world that we're moving to is one where we talk about smart acts, whether it's smart traffic or smart grid or whatever, where you basically have these decision sciences, estimation, prediction, control, optimization, that link both the data that you get from the real world and these mathematical modeling abstractions that tell you a sort of simplified view of the world. And you can kind of use these as orthogonal sources of information that allow you to have a better idea of what's happening in the real world than you would get if you only had your model operating without real-time sensor data. And certainly the model can help you fill in the gaps when your data might be corrupted, when your data might not be complete. So combining both the model and the data from the real system allows you the possibility not just to analyze and compute what's happening in the system, but actually use that information feeding back into the real transportation system. For example, controlling the traffic flow, helping users make better decisions. And these, because you're using complementary sources of information, your mathematical models and your data, you can help account for the fact that your model has errors and your measurements also have errors, and you might not perfectly know the inputs to your system. Where is the data coming from to help usher in better opportunities to estimate and control traffic? Well, the classic sensing technologies basically broke down into sensors that were on the roadway. One example is an inductive loop detector. It's literally a wire you put in the roadway. And as the car drives over that wire, you register a voltage change and you can count the number of cars. If you put two of them on the roadway and you know how far apart they are, you can also do things like try to estimate the speed of traffic. The modern version is wireless. It uses a magnetometer instead of a wire to detect the cars. But the main name of the game is count the cars and measure the speeds. The problem, of course, with putting the sensors on the roadway is that you've got to tear up the roadway to install them. You've got to tear up the roadway to repair them. So people have been interested in getting the sensors off of the road and putting them on the side of the road. That would be a video camera. That might be a radar unit that's stuck on a pole that's on the side of the roadway. And increasingly, and I think more relevant in this era of connected and automated vehicles, is thinking about the vehicles themselves actually as sensors. So the sort of antiquated version of that was putting GPS units on fleet vehicles like your FedEx or your UPS truck, and over huge commutes that those vehicles would operate, you could get information about the traffic conditions that they explored. That kind of pivoted more recently into tracking cars like taxis or Ubers or Lyfts, and including tracking you when you're driving your car with a navigation service on it. There are some other technologies that measure travel times. I really won't say a whole lot more about those. In terms of some of the classic and more modern ways to collect the data, the aerial surveys, we heard in a couple different variations, were basically this idea where you would fly over a freeway to try to get a camera up in the sky, and then from that camera, do some kind of image processing to get the trajectories or the paths or the positions of each vehicle over time and space, so that you could do things like plot what something called in the transportation community a time-space diagram. appropriately named. You plot the time on one axis, the space on the other axis, and then the line in this plot actually corresponds with the trajectory of a vehicle. And from this experiment that was done in the 1970s, flying a helicopter over a freeway in Ohio, they were able to do things like capture something that still eludes most traffic monitoring systems today, which are these traffic instabilities, these waves that seemingly occur without a cause, but quickly grow into a jam. The way that you read these plots, as the vehicle, the slope of the lines here correspond with the speed of the vehicle. So initially you have vehicles that move quickly, then they start to slow down. They encounter a wave where they actually stop moving. They retain at the same position over a block of time. The wave passes through them and then they start accelerating again. Okay. Capturing this type of feature from a real freeway was really only possible at the time by renting helicopters at extraordinary cost, putting cameras on them, pointing them down, and then doing extremely labor-intensive annotation of frame-by-frame video data so that this type of data could be extracted. So clearly great for extracting trajectories, but just completely unscalable. Where kind of a modern twist came in on that idea of getting that overhead view was from the NG-SIM experiment. In Benny's talk, he had the link to the data. Here is a visualization of that data. You can see the locations of each of the cars as time evolves in different lanes. This was captured from a video camera system that was located on a major freeway, Interstate 80 in Emeryville, California. And you can see on this bottom figure the different boxes that corresponded to the 6 cameras' fields of view. One of the pioneering experiments in the traffic simulation community, I think that data set has been cited probably 2,500 times at least in our community. And yet there are limitations, right? The data set that came from this experiment is 3 15-minute long data sets. There are a couple other data sets, one in LA, also on a freeway, and then 2 others that are on arterial streets. But generally, you know, this was a multi-year effort to pull this data out, partly because of the year in which it was done. You know, 2006, the quality of image processing, the quality of the cameras was much lower resolution. So it was still a very, very labor-intensive process to get that data out there. And so our field has really been inhibited by the lack of trajectory data to really understand some of these more nuanced features of traffic, like these instabilities that we captured with these overhead fields of view. So drones clearly offer some promise. The helicopter has gotten significantly cheaper. You can buy, you know, a cheap commodity drone, and if you're a licensed pilot, you can fly that and potentially collect some traffic data. There have been several teams that have been working in this area. The HID data set is I guess one of the more modern data sets that has this drone data set. You can see, again, it still suffers from the general problem we have with this type of trajectory data. It's only 420 meters long, but the video that briefly played there, you can see it does a great job of actually identifying the vehicles and identifying their speed. So it's starting to produce actual real data that can help usher in a deeper understanding of the traffic flow physics that, I mean, you might be thinking to yourself, why on earth do I care about how humans drive if they're all going to be automated? You should absolutely care, because all of the car companies that are trying to build automated vehicles desperately need to understand how you will interact with those cars. And it kind of put the pressure on a sore subject in the traffic flow theory community, which is that it's actually relatively challenging to get huge volumes of data about how humans drive at the level of this type of trajectory data. So there's an increasing push, not just in the traffic science community, but also in the automated vehicle community, to get abundant data about how humans drive. And realistically, we also not just want to know how humans drive in the absence of automated vehicles, but how they respond to automated vehicles that might not drive exactly like we do. So the HID data set is at least a step in the right direction. We now have the ability to fly drones overhead, get trajectory data, even though drones come with the standard limitations, right? You have limited flight times, and you're only able with a single drone to capture limited fields of view on the roadway. The number of data sets that are popping out now in the traffic science community is rapidly increasing, and that actually makes me quite pleased. There is a data set that came out very recently, within the last, I don't know, probably last month or so, that basically takes the drone data collection and puts a spin on it, and instead of collecting data on the freeways, actually collects data in urban areas. And I would encourage you to go download the data. I have not yet looked at it in detail, but you can see the natural types of things that we see, right? So 5 flight sessions for 2.5 hours per day. That tells me that we're running with, again, 30-minute flight times to do this data collection. So not a criticism of the data collection. It's actually a great thing that this data is becoming available and starting to help feed not just trajectory data on freeways, but also on the surface streets. But again, it's still going to have these general data availability limitations that we keep running up against. It's actually really hard to get data on huge spatially distributed systems that have, hundreds of thousands or more vehicles that pass through them at any given day. The way that traffic engineers have historically collected data is through these sensors that are on the side of the roadway. The inductive loop detector network in California ironically got its start, as I learned from a visit to one of the previous IPAM programs, got its start because people were freaking out about the fact that we built all these roadways and they were immediately getting clogged with traffic. And so they really started putting pressure on the traffic engineering community to go find out where the congestion is and what the cause was. And if you know anything about traffic, you know that the traffic is a consequence of an imbalance between supply and demand, but that result allowed us to actually get a lot of sensors in the roadway so that we could start to see how the network performs overall. So the system that drives the entire California sensor network is called PEMS. If you go to Caltrans, which is the California Department of Transportation, you can get access for free. You have to apply for an account, but it's readily available for anyone who applies to it. And so you get really good flow data, you get decent speed data, but it doesn't really have that high resolution trajectory data that you would really want if you're going to try to understand how humans drive on the roadways and catch some of these more nuanced physics features like stop and go driving.
And Dan, there's a question on the chat.
Sure.
Has there been data collection efforts on traffic with vehicles that have partially automated features?
Yes. I will expand on that shortly. That's a great prelude into a piece I did want to talk about here in just a second. So the inductive loop detector data, I wanted to make you aware that the PEM system exists. I also wanted to make you aware that there's a new data set called UTD-19 that was also recently released in the last few months that has inductive loop detector data, not just across the state of California, quite the opposite. It has 40 cities across the planet that you can get cleaned, processed inductive loop detector data. Again, haven't looked at the data myself personally, but really excited to see that this type of data is now available that can also answer questions that if you're only looking at one city at a time, you might miss. I'll skip the cameras. I think we heard a little bit, well, just to tie in an idea, the camera data has been around forever. Where it gets instantiated in the modern systems is for real-time traffic management. Major communities have these traffic management centers with hundreds of cameras that are all going into human operators that look and see. If there's a report of a crash, the operators will literally move the camera, zoom it into the spot where they think the crash is occurring, and confirm that the crash exists and alert emergency roadside services to go out and to support that vehicle. Still surprising how labor intensive and how human in the loop those types of systems are. The sort of pivot for the last 10 years has been this GPS data that collects not just over long time horizons, but continuously, like literally the speed and position of a car at least every second, sometimes faster. What that allows you to do is get these time-space diagrams where you get a whole lot more fidelity of the precise positions and speeds of the cars. But the problem is you only get it for a subset of the vehicles. Even companies like the Ubers and the Googles of the world are getting data from the vehicles that have their devices, whether it's their own Ubers in the case of Uber, or Google if you are running the competing traffic monitoring or traffic navigation app on your phone, you're not sending that data into that vendor. So they're only sensing a fraction of the vehicles. That's totally fine for some applications, but it doesn't really help a lot of the core traffic management applications like managing and throttling how many cars are on the roadway. Because what you really want to know there is the density of traffic on the roadway, how many cars are physically there, and based on the density of traffic, decide if you can let more cars on the roadway or not. So if you're getting great speed data, great travel time data, that's certainly helpful for navigation, but it's not actually helping the operators decide, can I let more cars on the freeway from this ramp or not? For that, you really want some of these other sensors that are on the roadway, like these inductive loops. Okay, so the question came up about what can be done with the driver assist systems. Well, here's an example of a stock vehicle, a 2009 vehicle that has an adaptive cruise control system on it. To run that adaptive cruise control system or variable cruise control system, basically it allows your car to speed up or slow down to match the speed of the vehicle ahead. That has a radar unit on it that actually can be read from the stock vehicle to do things like estimate how far apart the car in front of you is. So this is a dash cam video that is synchronized to another illustration that's showing you what the radar from this vehicle sees. And it's seeing, this collection of points here. It's seeing the semi-truck in the lane adjacent. It's also seeing the red vehicle that's driving ahead. So in addition to getting the spacing and speed data, you can get all kinds of additional information like the speed of your car, whether you're accelerating or decelerating, how far apart that car ahead from you is, and what the relative speed difference is between your car and the car ahead. The one that is really practical from a traffic engineering perspective is the space gap data. How far apart is that car from you? If you want to take this micro quantity, the distance to the car ahead, and convert it into a macro quantity that might help feed some of these partial differential equation-based models, well, the spacing between the cars is the inverse of the density and vice versa. So if I have the spacing data, the distance from my front bumper to your front bumper, then I can invert that to get an estimate of what the density of traffic is in my environment. Okay, it's an estimate because it suffers clearly from sampling error. You're measuring, one spacing and trying to extrapolate an aggregate quantity, the density in your neighborhood. But at least it's better than nothing. It's certainly better than only having speed data. And there have been works that have been conducted in the last 3 to 5 years that have shown that that type of spacing data, if you have access to it, can help improve the ability to estimate the traffic state compared to only knowing the speed data. So let me pause and actually see if I answered the question about what can be done with ADS data on conventional cars today.
Yeah, I got it. Thank you.
Okay. So I think just to put a final remark on that, I mean, that is an area that gets me extremely excited. I think, this is a completely underexplored area in the traffic estimation community, mostly because those vehicles, 5 years ago were luxury cars. And the systems, the adaptive cruise control systems, were features that you could, pay extra to have stuck on your already expensive vehicle. But companies like Toyota, Nissan, and several others are sticking this on every single car they sell. In fact, I'm not sure, but it would surprise me if you can buy a Toyota vehicle in the United States today that does not have an adaptive cruise control system of some form on it. So fine. When it's a luxury car company, I really don't know what to do with it at scale. When it's the world's largest automotive manufacturer, that suddenly gets me interested that this is no longer a boutique space in which could be. It's something that's real today, and we just need to start thinking about how to actually take advantage of it. Okay, so in the time that we have left, I want to basically give, call it 2 or 3 examples of what we know in the traffic estimation community and where it might be headed. The general traffic estimation problem kind of goes back to those box diagrams. I'm going to build some kind of mathematical model of the traffic flow, how it evolves in time and space, and I'm going to build that model based on properties of the roadway and first principles. And then I'm going to grab some real-time sensor data from what to be determined, and every time I make a prediction based on what the traffic is currently and what I think it will be in the short future, I will use that sensor data to correct my prediction based on the structure of the errors and the structure of the state given from the model. And this sort of model prediction measurement correction business has been around for a very long time in the transportation community. Generally, the measurement correction step is done with some variation of a Kalman filter. There's been works basically since the 70s that have explored this. I want to challenge you to look at the following two simulations that I've carefully constructed to show you why traffic estimation is a hard problem. So in this video, I want you to see on the top, there's some blue cars that are entering at a rate, okay? And these cars hit some traffic jam and slow down and then exit at some rate. And I'm telling you it's true. The rate at which cars are entering in the top and in the bottom are identical. The rate at which cars are leaving in the top and the bottom are identical. I give to you the following information. I give to you the rate that these cars are entering and their speeds. I give you the rate that they're leaving and their speeds. You tell me which one of the two settings you're in. Are you in the setting with the very short queue or the very long queue? I'm not allowing you to see anything inside the domain of interest. I'm only giving you information at the boundaries, but I want you to tell me the state inside the system. And obviously this is a trick question because you can't know. The boundary conditions for both of these simulations are identical. The traffic state estimation problem, when given sensor data like inductive loops that might tell you the count and speed information, the traffic state estimation problem is, given this time series of measurement data, can you reconstruct uniquely the initial condition or not? And the answer is you can't, because the initial condition is exactly the same as the current condition. These queues are not moving inside the domain. And it's showing some, fundamental property of these models that they're not reversible. You can't just take this boundary data and uniquely determine the initial condition, because the initial conditions are different, but the measurement data is exactly the same, and it will be exactly the same for all time. As a traffic estimation person, this really concerns me, because knowing where the queue is located, whether it's really short or really long, in surface streets is the difference between whether or not I need to turn this light down here green, or I can let it run red a little bit longer. In urban networks, you definitely don't want this queue to spill back all the way to another intersection. And if I can't tell where the current queue is located, then I'm really kind of flying blind in terms of when I need to change the signal. So this is a fundamental limitation of the traffic state estimation problem when you only get sensor data that occurs at fixed locations in space. You don't get any of that trajectory data. You just know stuff that's occurring at different locations in the network. This issue was identified most formally in this paper from 2003 by Roberto Horowitz and some of his students that basically showed that if you take the LWR partial differential equation, you discretize it, and then you take the discretization and chop it into a bunch of different modes, you can model these modes as a bunch of switched linear systems. And then for each linear system, you can identify whether or not the system is observable or not. And these settings that correspond to when there is a shock or a queue inside the domain are exactly the settings for which the state is not observable, meaning from the sensor data, you can't uniquely reconstruct that initial condition. Okay, that point has been further expanded upon and refined over the series of, maybe call it 15 years, where finally we got to the point where we actually do know bounds on the errors as you switch back and forth between different traffic states, ones that are free-flowing, ones that are congested, ones that have queues in the domain and one that don't. And if you like to see a lot more detail on these works, there is a comprehensive review article that just came out in the last 3 years that details basically the history of traffic flow monitoring from its origins to modern day. I'll maybe give kind of the bookmarks of the traffic estimation world. The origins date all the way back to the early 70s. This is the Lincoln Tunnel in New York City. There was a work that basically explored how to link at that time emerging systems theory concepts like filtering to real problems in transportation networks, like trying to figure out how many cars are stuck inside of a tunnel in New York City, specifically in the Lincoln Tunnel. And so here's kind of the setup that was used for the estimation problem. Basically, the tunnel was divided into 3 stretches there were sensors located at the breakpoints of each of those sections. And what they were struggling with is that basically they didn't have any idea how many cars were inside the tunnel. But at some point, traffic congestion would set in. And then once it set in, they couldn't get rid of it. And so they wanted to know how many cars were in there. So first, they could actually identify the breakpoints of when things started getting congested, but also so that they could ultimately limit the number of cars inside the tunnel so that the congestion could clear. And the way that they did it was about the simplest estimation problem one could consider. They considered a single state linear dynamical system that was ultimately solved with a Kalman filter. What they looked at is a specific stretch of roadway, okay, that had an upstream sensor that had a flow rate M in at time K and an outflow rate of M out at time K. And they directly measured those from the sensors they put in the roadway. And the state of the system that they tried to calculate was how many cars NK were in that stretch of roadway. And the dynamics of the system, well, are pretty straightforward. If you know how many cars are in the tunnel at time K, and you tell me how many enter, and you also tell me how many people left, then it's just simple mass accounting to tell me how many cars are in there at the next time step. It's literally how many were there plus the ones that entered minus the ones that left. Okay, and the key part here was that they directly measured those inflow and outflow rates. That's how they were able to make this a linear system, even though we know that these mass conservation models are nonlinear. The trick that I was really inspired by our kickoff lectures in terms of things that were already known a long time ago, the trick in this work that makes the whole system fly was this idea of a clever way to estimate how many cars are in the roadway directly as a measurement. And so here's the setup. They, on these sensors at the entrance of the section and on the exit of the section, in addition to counting the cars, they also had an estimate of the speed. They used those estimates of the speed to get a travel time for an estimate of the travel time for a vehicle that just left. So take this orange car that I've labeled in a time-space diagram. It took tau k seconds to travel through that stretch of roadway. If I know how long it took to travel through that section, I can go back in time on my inflow sensor and just count how many cars have entered after I did. If I assume that no one overtook me, and that's a big assumption, if I assume that no one overtook me, I know exactly how many cars entered after me that have not yet exited. So 3 cars entered after me. They must be somewhere on the roadway, here, and here in space. I know there's 3 cars in the system. Of course, noisy because I had this overtaking assumption. Of course, noisy because they didn't actually have the true travel time that we would obviously get today from any kind of connected car, whether it's connected via a phone or otherwise. But they use this idea of trajectory data implicitly to instead convert to an estimate of how many cars are in the roadway. That gave them the measurement they needed to correct this system and run a Kalman filter. So the full state space form, yeah, they put it in, the standard setup, the time dynamics, xk for your state variable, axk minus 1, the inputs bu, k, plus some noise process, typically assumed to be some Gaussian. The measurement equation is also stupidly simple. You are getting a noisy measurement of the direct count, a noisy measurement of the number of cars on the roadway. Through that sort of pseudo measurement, they kind of packed in through a travel time. But once you put the system in state space form, I mean, this literally becomes a linear system with a single state variable and a single measurement solved by a one-state Kalman filter, and it worked. I mean, not perfectly well, but I mean, especially given the time, I think surprisingly well. Well, this idea of using, trajectory data has obviously since grown, really anchored by the first really connected cars, which were cars that were connected with 3G networks and carried cell phones. There was a study led by Alex Bayan at UC Berkeley, grabbed 100 rental cars, stuck them all with emerging 3G-equipped, GPS-equipped cell phones, and drove them back and forth on a several-mile stretch of roadway in the San Francisco Bay Area. And the type of data that came from that experiment was this very high-resolution trajectory data, where the colors corresponding here to the speeds of the cars, the points corresponding to the trajectories of the vehicle, you can see in excruciating detail big traffic jams caused by crashes, but also some of these issues that we see in other videos like the Sugiyama experiment, where you have these kind of stop and go waves that are somehow emanating from a larger traffic jam up here, that if you look only at the aggregate data, okay, aggregate data from inductive loop detectors, this is the type of picture that you would see. You know, the resolution of these instabilities that happen in the flow are completely hidden from you because of just the granularity at which that data comes both in space and in time. So being able to peer into the actual trajectories of the vehicles is going to be really important for getting that sort of next level insights in terms of the behavior of these human drivers. Okay, just to show a little clip in terms of that these same type of estimation algorithms work. This was a far step up from a single state Kalman filter. Instead, used a variation of the LWR model where the roadway is discretized into probably about 100 different sections of roadway. Measurements are coming from cars, and those measurements are used to correct the state estimates. And then from the speed profile that the estimator tracks, one can estimate the travel time and compare that to true travel times as recorded from video cameras on the roadway. And the takeaway was that even 15 years ago now, it was actually quite easy to track traffic states using this trajectory data. That was actually pretty difficult to do with inductive loop detectors alone, mostly because of how sparse that data was. I think the last maybe, Joan, I don't know, do we have 10 minutes?
20 minutes until the stop. So
20 minutes to the stop. That's a perfect amount of time. The last example I want to give is one that's really tightly tied to automated vehicles, really pushing this idea of, well, if automated vehicles start entering in the flow, forget what level of automation. Do we need to change how we're doing conventional traffic estimation? And here's maybe more explicitly the conjecture. Traffic estimation today already deals with keeping track of the speeds and densities along the roadway for traffic management applications, irrespective of the fact that there are trucks on the roadway and that there are highly heterogeneous drivers on the roadway. There are good drivers and there are bad drivers. So if we start automating traffic by putting more of these vehicles with these advanced driver assist systems or full-blown self-driving capabilities, do we need to change the way that we think about traffic estimation at all? And one way to look at the problem is to say, no, we don't. We don't, because they're just a bunch of particles. And what I'm interested in is their aggregate behavior. And the nuances of the automated vehicles are going to be no different than the nuances of the human drivers. And so we can use the conventional models that we've been using for 50 plus years on traffic estimation. It's just the particles have changed their behavior, but not in a fundamental way. The exact opposite may also be true, that the way that those vehicles drive is in such a distinct way that unless we explicitly account for it, we're never going to get the performance that we need for ultra precise estimation in the presence of these vehicles. And so, it's actually relatively hard to set up real experiments to test that, but I'm going to kind of walk through a way that one could model traffic that has automated vehicles in it. We know a way to model traffic without automated vehicles in it. Just assume mass conservation using LWR. And then we'll run an estimator, one that accounts for the fact that there might be automated vehicles that drive differently in the flow, and one that doesn't account for it. And then we can explore the performances. If the performances are similar, we don't need them. If the performances are noticeably distinct, then one might want to rethink how we model traffic flow specifically for the problem of estimation. Okay, so again, the setup's going to be the same as we saw for the Lincoln Tunnel and for monitoring traffic on Bay Area freeways. You take the roadway properties. We're going to build some mathematical model of traffic flow. We will try two different models, classic mass conservation model and also a 2x2 system that accounts for vehicle automation. And then we're going to assume we get some data from the roadway, and we will use that data to make corrections from our model predictions, and we'll see whether or not running under one model that may account for automated vehicles gives you any difference in terms of the performance compared to the models that don't account for it. And so the general state space form, what we're going to be working with is we're going to have a state vector at time n, in discrete time, xn. Okay, that might be a, 50-dimensional state vector corresponding to the densities at different chunks along the roadway. And I'm going to have some mathematical model, some form of a discretized partial differential equation. It's going to take that state at time n and tell me what it looks like at time n plus 1. And of course, that prediction won't be perfect, even if I know exactly the state at time n. And those imperfect predictions, due to the fact that the models are imprecise and we might not perfectly have characterized their parameters, will come with some kind of model noise, here omega n, which has some statistics associated with it, right? A mean and a standard deviation if it's a Gaussian. I'll assume I get some measurements denoted by Zn at time n. Those measurements will not come from every single section of the roadway, but a subset of them. And they will be related to the state of the system through some measurement operator that will account for the fact that I am not measuring the full state, but only a subset of it. And I might not measure the state directly. If I'm getting speeds, for example, and my state is a density, then I need some mapping or some function that converts these densities back into speeds. Of course, the measurements are not perfect either. They have some errors associated with the measurements, and we characterize those errors with some measurement noise, here denoted nu n. Nu, of course, needs some statistics associated with it, like a mean error and a standard deviation, if we assume it to be Gaussian. So that's the high-level setup. Let's look at the models. Building off of the models that Benny had described in his talk, we'll start with the classic LWR model. From mass conservation, we see the partial derivative of the density with respect to time, plus the partial derivative of the flow with respect to x, or with respect to space, must cancel out. In other words, if you've got, I usually try to think about this as what is a negative spatial derivative with respect to flow? What is a negative spatial derivative with respect to flow? Well, that means I've got high inflow and low outflow. I've got high inflow and low outflow. That gives me a negative spatial derivative with respect to spatial derivative of the flow. I've got high inflow, I've got low outflow. What will happen to the density in between those points with respect to time? Lots of things coming in, not very much leaving. The density with respect to time has to increase. Okay, and so this model perfectly captures mass conservation, right? And the way that we close this model in the LWR model, we recognize that the flow is a product of the density and the speed, and the only trick is to write that speed not as an independent variable, but as a dependent variable, which depends on the density. Greenshields most famously closed this relationship by basically going out and collecting a bunch of video camera data to see how the density of traffic changed with respect to speed. Or you can think of this if you want to get in your microscopic traffic flow modeling world. If it's the density is the inverse of the spacing, I can look at how as cars get closer together, as the density increases, as the spacing decreases, the speeds must decrease. As I'm further apart from the car in front, I'm happy driving at a faster speed. And these are, empirically determined based on how humans actually drive. But once you have this velocity density model, then you can rewrite the flow not just as a spatial and temporal quantity, not just as the product of the density and the speed, but as a function of the density alone. And you get the characteristic fundamental diagram that shows you at low densities, you can add more cars on the roadway and still increase the throughput. But at high densities, if you add more cars on the roadway, you're going to start to reduce the throughput because of this concave shape that the fundamental diagrams all have. So that's the LWR model. All we need to do is take the density of traffic, regardless of whether it's composed of automated vehicles or humans, and figure out the average speed that all those cars drive at, and we can go ahead and run our estimator using the conventional LWR. Okay, the 2x2 system takes a slight pivot here. The 2x2 system, again, takes the classic mass conservation model that looks almost like the LWR, but instead of making the velocity a function of the density alone, we let the velocity be a function of the density and some property to be determined, okay? That property is advected along the traffic flow with some speed v. Okay, so that property actually stays with the trajectories of the vehicles. You look at a group of vehicles, you follow it through the domain, and that property is attached to those vehicles. Okay, and that property, unfortunately, you can see that it carries along with the vehicles in this equation, but it's not in conservative form. If you put it in conservative form, you get something that looks like this, that basically gives you, in addition to conserving mass, some type of conservation law for the total property. Now, this is relatively abstract at the moment, and I'll clarify it here in a minute, but what I want you to have in mind is that if the speed, v, is a function of the density and the property, then the flow, too, will be a function of the density and the property. right? In fact, the flow is just rho times V of rho, V of rho W, where again, that W is that property. So what we're going to do, instead of getting one fundamental diagram, which would be true if we only had one property, we'll get a family of fundamental diagrams, each characterized by a different property value. Okay, so what is that property? That property could be many things, including like whether drivers are aggressive or not. If drivers are aggressive, kind of intuitively, I would expect the roadway would probably tolerate more cars per hour being handled on a lane of road compared to if the drivers are all very passive and at 60 miles an hour don't feel very comfortable getting close together. If you want high throughput on roadways, the only way to do that is to move a bunch of people very close together at high rates of speeds. So aggressivity would certainly change whether or not we're on a fundamental diagram that has a high throughput or one that has low. Okay, but this property W can be anything you want. It's just a model, right? So one way to define the property, which I will define, I'll call the property a fraction of automated vehicles in the overall traffic flow. Okay, so the fraction, this property W, let it be 50% if half the cars on the roadway are automated vehicles. Let it be 20% if 1 in 5 cars is automated. Okay, but now this property has a very real meaning. And when I rewrite this system of conservation laws, instead of getting conservation of mass and conservation of total property, which I really don't know how to interpret, I get conservation of all the cars on the roadway, which definitely makes sense. And I get a second equation that says conservation of the automated vehicles on the roadway, which also makes sense. If automated vehicles are on the roadway, then certainly they should be conserved, not just in the absolute way, but for their specific class. So you really can see this actually as a two-class traffic flow model, which have been around for quite some time. But the key assumption to be able to say something like this is, remember, that property follows with those vehicles. So what you're not allowed to do in this type of model is assume that there is bulk overtaking of the automated vehicles over the human drivers or vice versa. That on average, the fraction of automated vehicles in a bulk of flow that's moving along the roadway is a constant. That's the key assumption for this framework to work. Okay, so once you make that assumption, then which velocity density curve you're on really hinges on how many automated vehicles you have. And the setup I'm going to use here is I'm going to assume that the automated vehicles have better control compared to humans. So they are actually comfortable driving for a given speed, for a given velocity. The humans want a larger spacing, lower density than the automated vehicles. They will accept a higher density, lower spacing to the vehicle ahead because they're using sensors and automation to respond to the vehicle ahead rather than you. Now, it's an interesting question, which I'll touch in our next tutorial, about whether or not that's a valid assumption, whether humans versus automated vehicles have more aggressive or more passive following separations. But for now, the assumption is that the automated vehicles have a lower spacing, higher density at the same given speed. So the more automated vehicles you have, the higher you will operate up on the fundamental diagram. Okay, to actually run the filter, we'll have to discretize the model. Just like in the LWR model, when one discretizes this with a Gounod scheme, you get something that looks, quite clean in terms of its interpretation. You look at the density in section I or segment I or cell I of the roadway at time n+1, and it's just the density of that same cell at the previous time step, plus a bunch of terms, but you read them as what went into the cell over the time step minus what left the cell over the time step. I mean, it's literally the same as what the folks at in the Lincoln Tunnel were working on. The only difference that between what happened in the Lincoln Tunnel and what is done in modern systems today is that we don't take for granted that we can directly measure the inflow and outflow of every cell. We assume that those are actually functions of the traffic state in the neighborhood. So in particular, if I look at the flow over the boundary into cell I, so it's really at the location I-1/2 to denote that it's going into the cell I. If I want to know the flow in there, I can rewrite it as the minimum of what traffic can be sent from the upstream cell. That's this S of rho function evaluated at I, what can be sent from the upstream section, and what can be received by the cell I+1, the downstream section. Here the R denotes the receiving function. So I claim that the flow over this boundary, over this cell boundary here, is the minimum of how many cars can be sent up here and how many cars can be received down here. And this is a well-known trick that dates back to Goodenough, but also to Jean-Patrick Lebec and de Gonzo. Sometimes it goes by supply, demand instead of the sending and receiving functions. But what's, I think, clever from a traffic engineering point of view is that you can build these sending and receiving functions directly from the fundamental diagram. So rather than solving Riemann problems and looking at the solution at x equals 0, which we see on the more mathematical talks, if you can build the fundamental diagram, you can calculate the sending function. It follows the free flow part of the fundamental diagram and then its capacity after that. So basically characterizing that when you don't have any cars in that upstream section, you don't have very many cars that can go through that boundary. But once you hit the critical threshold, in fact, it's called the critical density. If you're above the critical density in terms of the vehicles that are in that cell, you can send up to the capacity of the roadway. You clearly can't send more because by definition of capacity, that is the maximum flow rate that you can achieve on that lane. And the receiving function just is the opposite branch of that fundamental diagram. The receiving function takes capacity for low densities and then follows exactly the fundamental diagram. You read this as at very low densities, if you don't have any cars downstream, then you can receive up to as many cars as the capacity of the roadway. But once you get a lot of cars, you approach this jam density. At the jam density, the downstream cell is so packed with cars that it doesn't matter what the upstream wants to do. There's no place to put those cars. They can't enter. And so that's kind of how we rationalize or explain kind of the storytelling of what the math tells you anyway, which is that you can't send more cars than you have. You can't receive more cars than there's space for downstream. And the flow across the boundary will be the minimum of those two functions. Okay, the minimum of what can be sent and what can be received. That's the standard LWR model. For the systems models, we have
5 minutes, okay?
5 minutes, perfect. For the systems model, we have to write that second conservation law for the conservation of the automated vehicles. And then the sending and receiving functions are not just for one fundamental diagram, but you have to choose the fundamental diagram you're on parameterized by that property W, that fraction of automated vehicles. And so the flow across the boundary gets a little bit more complicated. It's still the minimum of some sending function and receiving function. But the nuance here is that the sending function is a property not only of the upstream density, but also the property of those cars. If they're not very aggressive, then you're going to send fewer cars over there. If they're really aggressive, then you'll send more. Okay, really aggressive here, I mean more automated vehicles. The receiving function is the same thing, but I have to be a little bit more careful in terms of what density I evaluate the downstream section at. I need to be very careful about accounting for how many of the cars of the cars that are entering will actually fit into that section. And so I'll just graphically show you very quickly that one can choose the right density to evaluate this receiving function at by doing some, again, storytelling that the Riemann solver would tell you anyway. So what happens to calculate this intermediate density that you need to evaluate the receiving function on is that you first let your cars in the downstream section, they move out of the way. The cars from the upstream section, they move into the cell. They match the speed of the cars that are in front of them, but they adjust their spacing in order to basically account for the fact that some of them may be automated and some of them are human driven. The fraction that move through, that fraction doesn't change, right? Because we assume no bulk overtaking. Once you do that, you have the right density to evaluate that receiving function is. You're really trying to evaluate based on the density of what these cars will take up when they move into that cell, keeping their fraction of automated vehicles. Okay, I will maybe very quickly go through how one can actually solve these estimation problems in the fully nonlinear setting. This is really particle filtering by pictures. It's a classic nonlinear estimation algorithm widely used in the filtering community. You basically keep track of your estimate of the state of the system X through a bunch of samples or a bunch of particles indexed by L. So X is 0, L is the collection of particles that represent my belief on the state of the system at time 0. For each one of those particles, it's very easy to propagate them to one time step in the future through my model with a realization of the model noise. So the orange particle went here, I evaluated it and got one particle at time n+1. The mth green particle, I ran through the model with a different noise draw, and I got a corresponding particle associated with it at the next time step, right? So I got a collection of particles at the next time step, and then I can grab my measurements and see which one of those particles, or which ones, actually match with the measurements I received. Some of the particles might not really align very nicely with the measurements you received, while others do. For the ones that don't align very well, you de-weight them. You say those seem to be unlikely. For the ones that match, you can increase the weight of those particles. And then to make sure you don't end up with only one particle with all the weight on it, you do some resampling where you basically more or less get rid of the particles that don't carry very much weight and get lots of examples of the particles that previously had a lot of weight. And so all the particles now have the same weight, but you've got more of the greens than the browns. Okay, that's your resampled state at the one-time step in the future that's been measurement corrected. You repeat the process. Okay, so once we have that, I'll just, I'm gonna have two remaining slides here. One is basically the general setup. We're gonna swap in our flow-based estimator. We'll run a micro simulation. We use the properties of the roadway to build our model and choose our parameters for the LWR and the systems model. We'll do those one right after the other. We use those models to estimate the traffic state, and we can compare, because this is in a simulated environment with automated vehicles, we will compare that to the true state of the system, and we will see that basically if the estimated state matches the true state better with the automated vehicle model, then we have a reason for keeping those models around. And if it doesn't, then we can run with LWR. And so here's just an illustration of what this looks like. We have 2 lanes of traffic. The red dots denote the human piloted vehicles and the blue ones denote the automated vehicles. On the left, we estimate the traffic state, the density along the roadway, as using only the LWR model. So it has no idea of what the fraction of automated vehicles on the roadway are. And then we repeat the same procedure, but we swap out the model used within the estimator to see that we can not only track the density, but also the fraction of automated vehicles on the roadway. This experiment basically shows that if the automated vehicle penetration rate is relatively constant, you don't need more complicated models. If that parameter W on the inflow doesn't change very much, the dynamics are exactly the LWR model. It's only when the inflow penetration rate of automated vehicles is more variable, you actually start to get benefits from using the systems model that directly accounts for the fact that automated vehicles drive differently. So the punchline is basically this. Like when we're thinking about automating vehicles, we really need to be asking ourselves, why are we doing this? I think there's plenty of good reasons to automate vehicles, but we need to be careful about which problems we tackle and why. I think the automated vehicles do provide a lot more data than the phones do, and really the time is right now to think critically about how to leverage that data. And this question about, well, if automated vehicles change the physics of the flow, then I think we may need new data sources to manage it. It really depends on how those cars are realized. And this is, I would say, the start of an open research area. So with that, I'll end today's lecture and be happy to take any questions either here or in the office hours following. Thanks for your time and attention.